And it's recording now. Now here's what I need to know from my folks at home. If, movement, is movement smooth or is it choppy? Nope. Well, is this movement smooth or choppy? Pretty smooth. Okay. Well, we'll just have to see what happens. I have no idea if the audio is going to come in. All right. Well, finally, at long last, I don't even know what time this bell is going to ring. It's okay. I scheduled 2 days on my calendar for this crap. So the homework isn't going to be due tomorrow, guys. It'll be due the day after. Okay. Okay. Great. All right. So we're going to start with fundamental identity. 8:13. Okay. All right. So I have exactly 30 minutes. We'll see how far I get. Like I said, I already planned on 2 days. We're going to start with the fundamental identities of trigonometry. And, I don't know if you remember from geometry, but the way we do proof type stuff is we establish some very basic truths and then we build upon those truths. We use those truths to prove that other things are true. So the very first identities are actually ones that we should already know. Uh, the reciprocal identities, sine and cosecant are reciprocals of one another. So if cosecant is 1 over sine of theta, which is something we already know and love, then it should be really obvious then that sine of theta is 1 over cosecant theta. I mean, they're just reciprocals of one another, right? Same thing is going to be true for secant and cosine. Look, if secant is 1 over cosine, then cosine must be 1 over secant. And if cotangent is 1 over tangent, then clearly tangent must be 1 over cotangent. Now, something that, again, I keep saying that Kai was the first to realize it, but Kai realized that, and he's not here, by the way, that tangent of theta is sine theta divided by cosine theta. You realized that a long time ago. Well, if that's true, then its reciprocal cotangent must just be this fraction flipped upside down, or cosine theta over sine theta. There's nothing even right in there. It's just to make sure that we all understand it. Everything's calm, cool, and collected there, right? Nothing up there was spooky. Okay. No screams of terror, so we will move on to the trigonometric identity, known as the Pythagorean identity. This is Pythagorean identities, but you'll see why in a moment. So we've learned in a previous set of notes, sometime last chapter, that in our unit circle, meaning radius is 1, that cosine of theta is just x, because it would have been x over r, but if the radius is 1, it's just x. And sine of theta, which would have been y over r, is just y because r is 1. So if you were to put these things on a right triangle, and I'm pretty sure I've done this before, I can't remember if I did or not, but I'm pretty sure I did. If the x value is cosine theta, and the y value is sine theta, then the Pythagorean theorem, which normally would have been a squared plus b squared equals c squared, or for our triangle, the equation of a circle, x squared plus y squared equals r squared, actually ends up being cosine squared plus sine squared, a squared plus b squared, equals hypotenuse squared, which is just 1. So what we end up with here is cosine square theta plus sine square theta is 1. Have I shown you this before or no? Okay, well, then that means I did it with my IB students. I apologize. I teach Trig to more than one prep. It's hard to remember who's seen what. But yeah, there you go. This is the Pythagorean identity for trigonometry. It is the trig identity. It's the most important. And almost every other trig identity is true because cosine squared theta plus sine squared theta is 1. And it doesn't matter what theta you choose. Let's just say 57 degrees. Yeah, cosine of 57 degrees squared plus sine of 57 degrees squared will equal 1. Neat, huh? I think it's pretty neat. That's going to come up often. And you'll realize often I also just say sine squared plus cosine squared equals 1. I'm just not saying theta, but obviously sine and cosine aren't numbers. So, but you know what's also pretty cool? This gives us identities for cosine squared and sine squared. All we have to do is isolate them by subtraction. So we could say, um, no, the hypotenuse is the radius, is 1. But we do have Pythagorean identities that involve tangent. We're going to get to those in just a minute. So cosine squared theta is just 1 minus sine squared theta. That's just by subtraction. You can do the same thing for sine squared theta. If you want to isolate sine squared theta, you just subtract cosine squared theta. Neat, huh? So there's 3 identities. Of course, this is really the only one of them that you had to memorize. And yeah, you will have to memorize this one, and you need to be comfortable manipulating this one to get to these two. You don't have to memorize these two, just know that you can manipulate this one. But speaking of manipulating the Pythagorean identity, let's go ahead and divide both sides of it by some other trig. That way we can get some more identities. So let's write the Pythagorean identity again. Cosine squared theta plus sine squared theta equals 1. And what I want to do is I would like to divide everything by cosine squared theta. Let's see what happens. Well, anything divided by itself is just 1, right? So cosine squared theta divided by cosine squared theta is just 1. And way up here we saw that tangent is sine over cosine. So sine squared theta over cosine squared theta, this is tangent squared theta. And from above and from our last chapter, 1 over cosine.
Why don't the powers cancel
out? X squared over y squared is not x over y, right?
Yeah.
That's why. 1 over cosine is just secant theta. So 1 over cosine squared is secant squared theta. So there is what's considered a Pythagorean identity. I don't have it memorized. The only one I've memorized is this one. And if I need the Pythagorean identity that involves tangent squared, I derive it. It's more efficient for me to know where it comes from than to memorize it. I do not have this memorized. The secant squared? 1 divided by cosine is secant. That's just from last chapter. So since there's 2 of them, it's squared. Oh, also, if you wanted to isolate, see here we have secant squared isolated. If you wanted to isolate tangent squared, you would just subtract 1 from both sides. Again, we're just manipulating identities to get other identities. I don't have these memorized. I do know, the only thing I have memorized is that there is a Pythagorean identity that involves tangent. That's the only part that I memorized. There is a Pythagorean identity that involves secant. That's the only thing I've memorized. And then I say, well, if I need that identity, I will build it like this. Is it going to take me more time? Yes. But I don't have to just memorize a bunch of crap. I hate memorizing a bunch of crap. It's too difficult for me. If you are good at memorization, by all means, start making flashcards. I am not good at rote memorization. See how much space I left? Hey, let's do it again. Only, I'm sorry? Yeah. I'm going to do this again, what I did here, but instead of dividing by cosine, I'm going to divide by sine. What this is going to do is it's going to build us Pythagorean identities that involve cotangent and cosecant. So this time we will divide everything by sine squared theta. Once again, I have not memorized any of the things that I'm writing other than cosine squared plus sine squared equals 1. And because I've memorized this, accidentally I've memorized these two, but that's just because you're just isolating one by subtraction. But honestly, all this stuff I'm writing down here, yeah, none of that is committed to my memory. If sine over cosine is tangent, then cosine over sine is cotangent. anything divided by itself is 1. And from last unit chapter, I don't know what just happened to my mouth, and the box up above, 1 over sine is cosecant. So this is cosecant squared theta.
Is this how this stuff would be written on the test? Or
What do you mean, what stuff?
like this, like proof stuff. How will it be written on the test?
On the test, it'll say, you know, this identity, I'm just going to hand you an identity, will say something like, is equal to one of these. Which one? And you just run through your basic identity proof type stuff and see which one it's equal to. You'll see. And then here, see, right now we're just providing the building blocks of our proofs. We haven't proven anything yet. And then here, again, I can isolate cotangent squared just by subtracting 1. So cotangent squared theta is cosecant squared theta minus 1. Woo! We have seen a bunch of identities already, haven't we? Wow, wow, wow. Try to memorize as little as possible. Understand where all the other stuff comes from. If you have trouble understanding where it comes from, well, then flashcards might be your friend. I do not like doing that, but that's just the way I learn. All right, are we ready to actually do some work? Nobody's freaked out? Well, maybe you are, maybe you're not. I'm not sure. Internal freak out. Okay, I can handle that. So this is a question that you've already seen, well, not this exact question, but this style of question you've already seen done and you've already been tested on it. I'm telling you, hey, I want you to find sine and cosine with given information about tangent and cosine. This is the stuff that we were doing before where I go, okay, this is 5 over 1. Let's draw the two triangles where tangent's positive and figure out which one has cosine positive. And, we've done all that before. But now I'm going to use identities. Do you have to use identities to do this style question? No. The way I showed you before is just as good as what I'm about to show you. I'm just a fan of showing you more than one way. So if tangent of theta is 5, can we all agree that tangent squared theta is 25? Just squaring both sides? Can we agree to that? All right. Let me creep up a little bit. Hey, here is an identity that involves tangent squared. It says if I add 1 to tangent squared theta, I have identified secant squared theta. So if I add 1 to both sides of this, 1 plus tangent squared theta is 26, then I can replace my 1 plus tangent squared theta with secant squared theta using this right here, something that we derived. Were you cool here? I took this and I squared both sides of it. That's how I got here. And then to get this line, I just added 1 to both sides of this equation. I basically did this. And that's how I got to here. And then I see that 1 plus tangent squared theta equals secant squared theta. It's a Pythagorean identity. It's right there. So I replaced this with something it equals. You see, now I can take the square root of both sides to isolate secant. If you square root both sides, you get that secant theta is plus or minus, don't you be forgetting the plus or minus now, is equal to the square root of 26.
So then 1 over 26 is get cosine.
Ah, and that's right. See, we were supposed to find cosine. So secant is the reciprocal of cosine. So cosine of theta must be equal to plus or minus 1 over root 26. And guess what? You were told that cosine is positive. Therefore, you ignore the negative sign, and we specifically just say that cosine theta is 1 over root 26. That was one of the two things we needed. We also needed sine of theta. Fine. Let's go back to what we started with. Tangent of theta is 5. But remember, tangent is sine over cosine. So again, replacing tangent with something that it's equal to, sine over cosine, 5. Now I'm trying to solve for sine of theta, so I'm going to isolate sine of theta here by multiplying both sides by cosine theta. So sine of theta is 5 cosine theta. But oh, wait a minute. This is what cosine of theta equals. So sine of theta must just be 5 over root 26 because we're replacing cosine of theta with what it equals, 1 over root 26. Was this easier than drawing the two triangles and using the Pythagorean theorem? Freaking no. But the point is, you could have done it this way, demonstrating that the identities work. Sir, what's up?
Why does 5 end up going on top of the fraction?
Because this right here says 5 times 1 over root 26.
Oh, okay.
And treat it as 5 over 1.
Yep.
So there you have using the identities. In my IB math classes, when they have questions like this, when I have to grade them, I'm given a mark scheme, and it says if they did this, then award points here, 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 and here, here. A question like this would have had more than one way of them doing it. The first way would have been drawing the triangles, identifying which one they had to work with, Pythagorean theorem, yada, yada, yada. The other method would have been using these identities because they're both equally correct. Talk to me. Remember, all your tests are going to be digital, so I don't know which method you choose. You could, but when you're doing your homework, I need you to do it the way that I'm doing in the notes.
This way makes a lot more sense than the other way.
Well, and that's the thing. For some people, this will make more sense because they trust and use identities. And if you can, awesome, go for it. I'm gonna be real with you though. I don't have this identity memorized, so for me, this method would have taken me a lot longer than just drawing my triangles. But that's a me thing because I don't do very well with just memorizing things. Okay, let's flip them over and see some more identities. Holy crap. Boy, that's a lot of identities. Now check it out. Do I need you to memorize these? No. I just need you to trust that they are true. We're not going to be proving them, I don't think. No, we're not going to be proving them. We're just going to be trusting that they're true. So these cofunction identities are true because of phase shifting and reflections. And that's why I really made sure that we took time to write equations of graphs in more than one form. That's why I described cotangent as a shift and reflection of tangent, things like that, because I was setting you up for this kind of stuff. All right. This says that a cosine graph can be found from a sine graph simply by shifting by pi over 2. And same thing over here, a sine graph can be found by taking a cosine graph and shifting it by pi over 2. Notice that it doesn't say theta minus pi over 2, it says pi over 2 minus theta. Why, Mr. M? Because if it said theta, it would have to say theta plus pi over 2 is why. So why do mathematicians decide to go with this form? I don't know. I'll be honest with you. It just is. Now tangent and cotangent, maybe that's why. Maybe it's because in order to get a cotangent graph, you have to shift and reflect the tangent graph. Maybe that's why. So what you're looking at here is, since it's in the wrong order, it is both a shift and a reflection, because remember, you put that minus sign on the theta. This is a reflection over the y-axis. Maybe that's why, because for tangent and cotangent it was very, very obvious. But basically it just says, hey, every function can be found using its co-function, every single one of them, by shifting pi over 2 and reflecting. Isn't that neat? That's all it says. You just simply shift pi over 2 and reflect that bad boy over the y-axis. You got your co-function. Boom. And remember last chapter, we talked about the even and odd functions. Hey, look, even and odd identities. There they are. Because sine is odd, reflecting over the x-axis, reflecting over the y-axis is the same as reflecting over the x-axis. Same thing is true for cosecant, since it's just the reciprocal of sine. Since cosine is even, reflecting over the y-axis is the same as doing nothing, which must then be true for its reciprocal as well. And since tangent is odd, reflecting over the y-axis is the same as reflecting over the x-axis, which must also be true for its co-function. And that's why you had a test question last chapter that said, which of them is even, which of them is odd? Because I needed you to know that for upcoming material. Cool with this stuff so far? Just getting blank stares. People aren't even nodding. That scares me a little bit. Has something happened that we don't understand? So are we all cool so far? Yeah? All right. So let's go ahead and use some identities. I'm telling you that cosine theta is equal to 0.34. And I'm asking you to find sine of theta minus pi over 2. Okay, wait a second. Sine of theta minus pi over 2. That is dangerously similar to one of the identities that is up here. It's dangerously similar to this one, isn't it? But look what's happened here. The order of these two things is backwards. What changes the order of the inside? What changes the order of anything in mathematics? If I want to change an x minus 1 to a 1 minus x, what do I have to do? Not inverse. You multiply by negative 1. So let's start with this, and let's start using identities. So we have sine of theta minus pi over 2. Now multiplying by negative 1, can we all agree that's the same as dividing by negative 1? We cool with that idea? Okay. So then everybody in the room is comfortable with me saying that that is equal to this. And by, when I say everybody in the room, I mean people at home as well. So I just factored out a negative 1, which is division. If we did this, and on my notes I actually wrote what happened here. This was just factoring. And hey, isn't sine an odd function? So multiplying by a negative sign on the inside is equivalent to multiplying by a negative sign on the outside. Because sine is odd. Okay, but my box up top says that sine of pi over 2 minus theta is strictly equal to cosine. So this is strictly equal to negative cosine of theta. We know what cosine theta equals, so I guess we know what negative cosine of theta equals, don't we? It's just going to be negative times the value that cosine theta is. Negative 0.34. There it is. And all that was because of identities. And I'll get through one more question. This next question just says to simplify the expression. Holy guacamole. Look at all of that stuff. if I was told to simplify this, what do you think my first step would be? Factoring is yes, but not x. I can't take x away from sine or cosine. Yeah, I could factor out a sine of x. So let me,
to make cosine more of the whatever.
well, no. Let's just factor a sine of x out of both of these things. If I take a sine of x out of sine cubed x, it's going to leave me sine squared x. And if I factor the sine x away from sine x times cosine squared x, it's just going to leave me cosine squared x. Wait a second. What is sine squared plus cosine squared? It's 1. This is the Pythagorean identity. Sine squared plus cosine squared is 1. So this says sine of x times 1, which is just sine of x. So all of this stuff, sine cubed x plus sine x times cosine squared x, is strictly equal to simply sine of x. Isn't that neat? Now, unfortunately, I don't have time to.
Do you need a placeholder 1 in there?
No, what's sine of x times 1?
1.
No, it's just sine of x. Done. This is multiplication.
No, I was talking about in the middle because there's no.
What do you. No, this sine of x is one thing.
Okay.
Okay? Sine of x is some number we don't know. So we just treat it as a value. You can do up in the homework, you could do up to number 26. That's how far we got. Yes. You need to understand why they're true. I don't need you to memorize them. Because if you understand why they're true, then you'll see when they're useful.